Make some comments about to whatever extent we can understand holography in the SYK model. And this is work which is based on Antal Yevicki and his student Kenta Suzuki and my student Animi Ghosh. These are some of the papers, and then I'll talk towards the end. I'll talk about some work which is in progress. So typically the examples of holography we know of involve some large N field theories, some large number of degrees of freedom in some sense, and sort of generally believe that somehow the large N degrees of freedom get sort of undergoes a metamorphosis in which they appear as some additional dimensions. In most cases we do not know well the details of this metamorphism, and there are some exceptions which are not as interesting as the examples from, for example, from string theory which we know of, but nevertheless do serve as important guidelines into how we might be able to understand this. And these examples involve vector models and probably the earliest examples, which is matrix quantum mechanics. This talk will use some of the lessons of those examples to understand an interesting toy model which is being discussed quite extensively in the recent couple of years, and where we believe there may be a chance of actually understanding how large N leads to holography. The type of as we will see, this particular model after a certain step becomes a class of models which in which fields appear in vector representations of some large N group, and perhaps the earliest example of such a model which leads to holographic correspondence is the famous work of Klebanov and Polyakov, where the conformal ON vector model was sort of argued to be dual to higher spin gauge theories of the Vasiliev type. And at that time we made a proposal which in its original form didn't quite work, but let me tell you what the proposal is anyway. So the idea is that since it's a vector model, all invariants can be obtained from bilocal fields because there is only one index to contract. And so the idea was that you form out of these the original vector fields a bilocal object, which I'll denote by sigma, and make a change of variables from the original fields to the bilocals. So now you introduce center of mass and a relative coordinate, re-express the relative coordinate in terms of kind of the radial variable, which is the magnitude of these relative coordinates and a set of angles, and you expand that bilocal quite trivially in terms of these generalized spherical harmonics. So the coefficients now appear as objects which are now fields which are a function of this center of mass and the magnitude of the relative coordinate, and the spherical harmonics give you the dependence on the angles. So our first instinct was to identify R with something like a Poincare coordinate in d+1 dimensions, and then the fields, these labels which are the angular momentum labels on these angles, would be the labels which denote the spin in the higher dimensions. So you get a theory of infinite number of spins, and these would be somehow be related with these massless higher spin fields. If this were completely correct, then the conformal transformations acting on the 2 points of the bilocal x and y, or equivalently u and v, should reproduce the Killing symmetries of the ADS d+1.
So this would be ADS d+1 cross S max.
cross SD minus 2. But the SD minus 2 just become, reduction on that has become the higher spin things. So let's see to what extent that works. It actually works quite trivially for dilatations, translations, and rotations, as you can easily check. So for completeness, I've written down what the action of these leads to on this bilocal field sigma in terms of the u's and the v's. As you can see, for dilatations it's quite trivial, translations it's quite trivial. For rotations, there is a piece which I call Lij, which is the angular momentum generator in the space which is spanned by the relative coordinate, and that's of course the effect of the spin which acts on this. And these of course agree with the isometries of ADS-D plus 1 acting on fields of an appropriate spin. However, for arbitrary D, this does not work for the special conformal transformations. So I have written down what happens for special conformal transformations on this bilocal object. The first line is what you actually expect for that appropriate spin object in ADS-D plus 1. The second line is something troublesome, and it is troublesome in a very fundamental way that it actually mixes up fields with different spins, which it shouldn't do if it were going to act on definite spin representations in ADS-D plus 1. So I'll tell you how this gets corrected, but that's not the subject of this talk. But let me point out something interesting actually happens when you have D equal to 1, namely you start out with just quantum mechanics as the boundary theory. So this is a repetition of what I just did for D equal to 1. In this case, the group is SL2R. So x and y have these L minus 1, L naught, and L plus 1s for each of those. Rewrite those in terms of the center of mass and the relative coordinate, and you get these for that, this for this, and that for this. And these you realize are exactly the Killing isometries of a Lorentzian ADS2. That extra troublesome term which appear in the special conformal transformation is simply not there because there is no spin. Okay. Now this is a bit funny, but because starting with one dimension, of course there is nothing Euclidean or Lorentzian about that, it's just one dimension, but you are always forced into a realization where the effective metric which appears in this bilocal space which I have written down is always Lorentzian.
In general dimensions, if you drop that funny term, you also got Killing isometries of Lorentzian?
I was comparing it with the Euclidean. I mean the thing I was doing Euclidean, so when I said it doesn't work, it didn't. In fact, in our original paper we noted that this happens, but we thought this is some nonsense, so we just didn't care about it. Okay.
Sorry, I didn't understand. So up to that spin term it works for the
Euclidean. If you start with, I think up to that term, if you start with Lorentzian, you get Lorentzian ADS. If you start with Euclidean, you get Euclidean ADS. That additional term in the D equal to 1 makes everything Lorentzian.
It doesn't vanish.
It doesn't vanish.
It's there.
It's there, but it just adds up to the other thing. I mean, the difference is a difference of sign somewhere, and somehow it just happens.
So then, Javiscian collaborators and
I'll come to that. Yeah, I'll come to that.
They seem to match eventually, but is that to an
Not with these identification. They do something different. Let me just come to that. Okay, that's the next slide. Vesalius theory is supposed to be dual to a gauged version of the 2 plus 1 dimensional model, for example, which you can do with a Chern-Simons gauge field. If you work on a plane, there's something simpler which you can do. In this case, the gauge version, in acting on a plane, it means you restrict to the singlet sector of the model. And what that means is that the bilocals have to be at equal time bilocals. So you have to work in some kind of Hamiltonian framework. So that's sort of intrinsically Lorentzian, if you wish to say. And for d equal to 3, what these Robert, Joao, Antal and Jean, what they did, they invented a non-local transformation such that in a light front quantization, such that the symmetries work exactly the way they are supposed to do. Okay. So basically what they did, they said that, okay, I take a function of this t and of these x's and the z's, and I invent a transformation on that such that on the new fields, these the original conformal symmetries in fact give rise to the correct isometries of ADS. Unfortunately, in order to do that, they had to go to the light front quantization. The reason is big that they have to get rid of all the gauge modes. I mean, work entirely in terms of the propagating degrees of freedom, and they could this map. And as far as I'm aware, I don't think anybody really satisfactorily could do it even in canonical quantization. I don't know the reason why. It could be a technical thing, and certainly not in a way which keeps the gauge invariant.
The bilophils would have a Wilson line connecting.
If I think if you have on a plane, I mean that Wilson line actually doesn't do anything. I mean there's no non-trivial holonomy on a plane, so I think you can set you can just forget about the
Maybe a k equals infinity. A non-trivial k.
Could be k equal to infinity. Yeah, I think so. Yeah, yeah. Right.
Sorry, and just going back to the original covariant construction, there's no way of correcting it, adding nonlinear terms or something.
I tried for a while, but no, not that I know of as anybody is able to do that actually. Yeah. In terms of in terms of the not the general. Yeah, yeah.
Very near.
It looks very near, and every 5 years I try a little bit, but I haven't been able to do that. But we will see an interesting twist on this Lorentzian business for the equal one. Yeah.
So I was just wondering whether it is covariantly.
Just in the path integral.
Yeah,
That's
so
just
it's
what I
like
will do now. Yeah.
It almost works. Something didn't quite work, so some theory definitely.
Yeah. But the something is a little bit, I think, telling you something, because it mixing up things of different spins. And so I think in order to correct it, it does, I think, require again some non-local, transformation. And I don't quite understand the physics of that. Okay.
So you just try to guess some variables that would replace
Yeah.
Vassiliev's theory and vice versa.
Yes, that's right. These people basically took the equations in the light front gate, took the equations which implement the isometry and just matched things so that it works.
Can they
Yeah.
show that they get Vassiliev's equations for that?
Yeah, up to cubic order, I think they can show that they get the Vasily. So they calculated I think up to the 3-point function, and they showed that it works. It works, but I don't find it very elegant, and it's probably not the right way to proceed.
It's because it has UI tangent BI, where tangent BI is with angular.
That's right. That's right. Yeah.
So suppose in general I expect a strongly coupled quantum theory to be equal to have a equal delta zero. Lagrangian description may not make sense, right? So how will I make, what is the meaning of in those cases the construction of bilocal?
If you have a Lagrangian strongly coupled, there's a coupling in the Lagrangian, it's strongly coupled, what's your problem? I'm starting with a Lagrangian.
But I mean, in general, we know that quadratic may not make sense. Fields may not make sense sometimes.
Which side are you talking about?
I'm talking in the case of boundary, in the field theory side. And
You're saying there are strongly coupled field theories which don't have a Lagrangian description. That's what you're saying.
yeah, that's the point.
But there are strongly coupled field theories which have a Lagrangian description, like UCD.
Yeah, so I'm just asking as a general principle, just constructing a path dual out of this.
No, there's no claim that there's such a general construction here.
So what is your worry? Your worry is that if start with a particular Lagrangian
Yeah.
in the boundary.
Yeah, so which is like, yeah, that's right.
And you're worried if the Lagrangian is so easily solvable, why should it have a bicycle? Is that the question? Yeah.
No, I thought you were saying that this entire method of whatever I'm going to take,
Yeah.
why would it be generally applicable to strongly coupled field theory? Because we know there are strongly coupled field theories, we don't have a Lagrangian description.
Right.
I thought that was your worry. Am I
That's
correct?
one,
No.
but,
Yeah.
but in general, say I'm just asking, say I have a 5-port theory, I go to the critical fixed point. Which
Yeah.
are the
Mhm.
residual. How do I write down a Lagrangian at that point?
This is a Lagrangian.
I start with the probably some, how will I start doing the some kind of manipulation as we're doing here?
Lambda 5 to the 4, solve at large n.
So I start with the free description and then somehow try to take the
No, large n. You take lambda 5 to the 4, solve it at large n. That's what, I don't know, Ma or whatever did in the 70s. Calculate whatever you want to calculate.
Critical load.
Yeah, critical. Wilson-Fisher theory, right? Yeah. 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 Okay. Try this. So, as I said, this, nevertheless, this has become useful in a discussion, in current discussions of the SYK model, and let me point out how, give you a,
One more comment.
Hmm.
You know, you would get a Lagrangian for your bilocal.
that's correct.
There's no known Lagrangian for Vassiliev. So if you could actually do it, you could actually learn something about Vassiliev.
Yes, I mean that was the idea. That was the idea, to construct a Lagrangian for the Vassiliev theory. And what these people did was to do that in a very limited context of working on a plane and going to light front quantization. Yeah. So off-shell Lagrangian for that. Yeah.
Sigma and G in SYK is,
Hmm?
in SYK there is this bilocal field G and sigma.
We are going to use one of them, only one. Yeah. Huh?
This G is going to be the field that you are talking
That's
about.
right, yeah. That's
In
right.
SYK.
That's right. The formulation which we use is what you would get by integrating out the sigma.
Yeah, first then you get a non-local action.
That's right. Yeah. Well, the other one is also non-local.
The other one is also.
No. Okay. They're quite equivalent. I find it easier to think of it in these terms. So this is a quantum it's not quite a quantum mechanical theory because it has some random couplings with some Gaussian distribution. However, when n is large, one can treat this using replicas, and what Sachdev and Kitaev showed that this averaging over J can be thought of in fact as an annealed averaging rather than a quenched averaging. That means you can just treat J as dynamical fields in the action. I understand this works up to order 1 upon n to the 4. I mean, I don't know the details of that, but it certainly is not going to work for a finite n theory. I mean, for n equal to 5 or 10. Okay. So that's the context we are going to use this for. So once you do that, of course, what you will get is a non-local thing in Euclidean time. This is all Euclidean. So the interaction terms give rise to something where you can write it as some bilocals raised to this some power q. Q was the number of fermions which were interacting with each other to begin with. So given this form of the action, it's obvious that a nice way of dealing with this problem is to again make a change of variables to these bilocal objects which I have talked about. So this was done by Jibiki, Suzuki and Woon. It's a kind of a reformulation of results which were known in terms of this. So doing that, of course, you get this crucial fact that making a change of variables, you get a non-trivial Jacobian, which is represented by this kind of term. The trace means that I treat psi as a matrix in T1, T2 space. Those are the two indices of psi. And the rest are just rewriting of the original action in terms of this psi.
Psi was the bilocal psi dagger.
That's right, yeah. Well, there's no dagger, but I think just psi, yeah. Okay. So it's an anti-symmetric thing in T1 and T2. Good. So what does this action do? At least in large n, what this action, large n and small perturbations around the saddle point, this is going to give you, generate the entire theory. All correlation functions can be obtained as in usual quantum field theory, except that this is a pretty complicated stuff. Okay. In particular, the equations of motion which you obtain by varying psi from this action are the standard Dyson-Schwinger equations. In fact, an efficient way of finding out what the Jacobian is to in fact demand that whatever you get gives rise to the correct Dyson-Schwinger equations. That's how it was originally done. At strong coupling, or in other words, I mean, if you are working at 0 temperature at times which are J times tau being very large, if you are working at finite temperature, J times beta being very large, you can ignore this term, and as was noted by Kitaev, then this action or this equation of motion acquires a new symmetry. Okay. I should point out one thing is that before doing the averaging over J, there was no ON. I mean, there was all kinds of indices which are contracted by the J's. The emergence of this global ON symmetry comes only because after you have done an averaging over the couplings. That's when the ON symmetry also emerges. And at strong coupling, you can ignore this term. This has the well-known reparameterization symmetry going to an arbitrary function of time. In that limit, you can solve the saddle point equations, and this is the 0 temperature solution with some numbers out here. And as you would do in any quantum field theory, you would start by taking this bilocal object, expand around the saddle point, and calculate the action up to quadratic order, cubic order in the zetas, and calculate whatever you want to calculate.
So if you could go back to
Yeah.
previous question.
Yeah.
So the last term,
Mm-hmm.
sorry, you said how you get that from the variation of that. Like for instance, why isn't the homogeneity in psi decreasing by 1 when you vary?
Also, when you vary this thing, so there is a 1 upon psi there. What I have done here, I have multiplied by that psi here. Okay. Good. And as is usually the case in quantum field theory, in order to calculate things, what you need to do is to expand the fluctuations in a suitable basis. Okay. In this case, because there is a large symmetry in the strong coupling limit, the choice of the basis functions, and this is very crucial in Kitaev's argument, is actually entirely dictated by the SL2R symmetry of the problem. And that choice is as follows. So basically what happens is that when you do the expansion, you get an action which has 4 integrals, eta and a kernel and another eta. This kernel can be simultaneously diagonalized with the SL2R Casimir because of the symmetry. So you have the good thing to do would be to choose eigenfunctions of this kernel and simultaneous eigenfunctions of this kernel and the SL2R Casimir, so that you can diagonalize this entire action.
Actually, when you do the mode expansion around the saddle point,
Uh-huh.
then you have to isolate the collective mode.
I'll come to that. Okay. Good. Those eigenfunctions can be written in terms of this t and z, which are this, if you recall, are the t1 plus t2 and t1 minus t2, maybe by a factor of 2, in a particular combination of Bessel functions, which is displayed out here. Now, Bessel functions are well known to be eigenfunctions of the SL2R Casimir. SL2R Casimir is also related to the Laplacian in ADS2 or whatever. This particular combination of Bessel functions is sort of forced upon you by the fact that you want this to also diagonalize the kernel, and that's a bit of a subtle business which I think was pinned down sort of nicely, and I don't know the complete details by Polchinski and Rosenhaus, that this is the combination which has to appear.
Sorry, one more immediate question.
Hmm.
I think like Indrani was asking at the beginning, is the action you wrote down in terms of psi equivalent to the action in terms of psi and sigma after integrating out sigma?
It should be. I mean, I haven't checked it really, because if you write it in terms of psi and sigma, there is a determinant of Pfaffian of del t minus, that has to be expanded, and I mean, I don't know how it really works, but I mean, it should be, because at the end of the day you get the same Dyson-Schwinger equations. Yeah. Good. So this is exactly what I said. These are the eigenfunctions. They appear as eigenfunctions of a wave operator of a scalar field in ADS2 exactly at the BF bound mass, because that's in fact the SL2R Casimir, and these are the normalization and the completeness conditions for these things. Yeah.
So wouldn't the sigma equation just tell you that 1 over del t plus sigma is psi, and therefore whatever appears
The sigma equation means the equation which you obtain by integrating out the sigma.
by varying with respect to sigma.
I thought that just tells you that psi, I mean the bilocal is psi, right? Because sigma was the Lagrange multiplier, right? Yeah.
So the bilocal, which is what you call psi,
Mhm.
is 1 over del t plus sigma, is the property.
Ah, I see, okay, that's right.
And
Yeah.
then you put that back into the determinant, you get
Probably you probably get this thing. Right. Yeah. Yeah. Good, good. Okay. Yeah. Okay. And at the end of the day, due to a heroic calculation by various people, you obtain this action. And in this action, you get this horrible function of nu. Nu is an object which was the order of this Bessel function, which was related to the eigenvalue of the SL2R Casimir. So the spectrum of the theory is given by setting this to 0. So the equation where this object is equal to 1. Okay. Now this is a pretty complicated transcendental equation. It always has an infinite number of solutions for any value of q. However, there is one particular number which is always a solution for any q, and there is a reason for that, and the reason is that this is actually at strong coupling, this is a 0 mode which comes from the reparameterization symmetry, which is broken by the saddle point. So I said that strong coupling there is a symmetry. The full theory does not have this symmetry. So since this is the strong coupling spectrum, it should display that that is always a solution. The Pm equal to 3/2, remember this nu was the order of that Bessel function. So if you put j equal to 3/2, the j 3/2, with a little bit of calculation you can just show that if you take the saddle point solution, make a infinitesimal reparametrization, you will get this j 3/2, just, and that's why this happens. Okay. Good. I will talk more about this 0 mode in a while. Omega was the Fourier in time, so I wrote the thing in terms of e to the I omega t. The time is t1 plus t2 by 2. Okay, so this is how you might want to solve it. For q equal to 4, it's a not so bad equation. It's something involving trigonometric functions. Good. Now, looking at this, you might think this object phi, which was the fluctuation of the around the saddle, looks like a function of two variables, t and z. So you might think, okay, this is some field, some field which is in the theory. However, this cannot be a conventional field, because if you look at the action are written in a rather perverse form in position space. You see, it has some complicated function of the square root of the Laplacian. So it contains all derivatives of the Laplacian. which gets reflected in the fact that the spectrum of the theory, if you think of the spectrum of masses of the theory, there is an infinite, tower of the theory. Okay.
Kappa tilde of good dB means you put good dB in that bunch of
That's right. In that expression with gammas and interpret it in some way. Okay. Yeah.
and someone expects the gamma functions is fine infinite number of fields.
Hmm?
How do they know that that combination of gamma functions is the propagator of an infinite number of fields?
Because the solution of that equation kappa tilde equal to 1 has infinite number of solution. So those would be the poles of whatever propagator you have. So it should have an infinite number of fields. Okay. Yeah. What the dynamics of this we don't know yet. We'll come to that. Okay. So as I said, in fact, written in this way, the propagator looks like a sum of contributions from an infinite number of fields. And the conformal dimensions of the corresponding operators are given by these objects H, which is half plus P. P is the same as nu, the solution of that equation.
Really sorry. Just
Can you go back? The variables T and Z were, T was like the sum of the two sides.
That's right, yeah.
Z was like, what was Z? Oh,
The
it's
difference.
back to that.
Same thing. 2 points. The difference is Z and the sum is T.
Sorry, why do all of them have the same mass?
Hmm?
Why do all your fields have the same mass?
They don't have the same mass.
Your dB has a plus 100 version of the mass.
What? Where?
Uh,
Yeah, but you have to solve this equal to 1 equation. So I think, whatever it is. Good. So given that you work a little bit more and you calculate what the bilocal propagator have, and you get an expression like this. Whenever I write integrals over this d nu, that actually means a sum and an integral, because representations of SL2R have as the continuous series imaginary numbers and the discrete series. That's what it gets reflected in. And perform all the integrals is a long story, and you get an answer which looks like this. Okay. In this answer, I have integrated over the nu, so I have written everything entirely. In a sense, it's like an on-shell propagator. But what I meant is that it only has an integral over omega, which is the the energy, and the rest have been integrated over. This kind of thing always happens when you do integrals over Bessel functions. I mean, when z is greater than z prime, you get one thing, z less than z prime, you get another thing. This object is the residue of the pole which comes from here. In going from here to here, I have done some contour integrations to change that. So I obtain a residue of that pole. If you want to know what the residue of the pole is, it's horrible. This is what it is. There is an explicit expression for the residue of the pole. And this NPM, this is a normalization factor which just tags along with those Bessel functions. Okay. Everything is known in this formula. I should say that I have actually cheated a little bit, even though if you do not cheat, you get the same answer. It turns out there is a double pole at 3/2. This PM equal to 3/2. What I have done is that in anticipation, what I have done is that I have shifted the pole at 3/2 by a little bit, and the reason why I want to shift it by a little bit, at this stage it is just like a regulator. Physics wise, it comes from the fact that once you take into account finite j corrections, 3/2 is no longer a pole, and it gets shifted by an amount which order 1/j, which can be calculated. Once you do that, you get this expression.
This first line, second line is pretty similar to what Karen wrote in that, because it's all mathematics.
It's all mathematics, yeah. It's I mean, first line to second line is contained in various appendices of Polchinski and Rosenhaus in a way. I mean, implicitly, not in this language, but it is not done in the cross ratio versions as Maldacena and Stanford does, but in terms of the z and t, which is equivalent anyway. Yeah.
Very basic question, which is the breaking of radius to symmetry is kind of crucial for the SYK model, and that is because you have the additional scalar field
Absolutely, yes.
So, are you hoping in your bilocal degrees to somehow manufacture both the ADS2 and its breaking?
Yes, yeah, I'll come to the breaking. Okay. I'll turn into language which is our language. You can do the breaking without going to that interpretation. So, okay. The answer I wrote down is of course divergent, because at nu equal to 3/2 this object is divergent. There is a factor here which becomes infinity. Okay. At finite coupling, of course, there is a calculation by Maldacena and Stanford, who calculate the effect of perturbatively in 1 upon beta j effect of what happens to this particular pole, and you find an answer which looks like this. Okay. Once you use this answer in that expression which I wrote down, which was sort of understood as something which is with a shifted pole, you get this quantity, and this quantity is exactly what is called an enhanced propagator, because it is proportional to j rather than order 1, and it is this quantity which is the meat of the story, because it is this quantity when analytically continued in a particular way gives rise to the Lyapunov behavior indicating chaos. Okay. And it is this quantity which in a different way of looking at it comes from the Schwartzian action.
So for the mode number 3/2, this is become trigonometric.
These are J3 halves. If you want to treat that mode separately, right, so you will get a 3/2, J3/2, and then you write like the usual calculation, right, you write psi naught, which is 3/2, and then plus epsilon with times, rather you get, yeah, so you take the original thing and then epsilon of delta epsilon psi naught, plug it into the psi thing, right, and then you get a j/2, J3/2, J3/2, epsilon epsilon. You contract the epsilon epsilon using the Schwartzian action, and then you get this answer. But I think it's the same thing. What we defined here. Yeah. Yeah. Huh? Everything is Euclidean. Yes, you have to do that and do that analytic continuation to get the chaos thing. Mm-hmm.
They have some psi 0, psi beta by 2, psi 0, psi beta by 2, but they do some UV regularization as well. Some particular UV regularization that they do. You don't have to do something.
Well, this is exactly the same answer of Maldacena and Stanford. So you do whatever they have done. I mean, I don't know the details of that. Okay, yeah, I'm sure you have to do that. I think. I mean, it's exactly the same. There's nothing different here. Okay. So these are like, so there is a 1, 2, so t plus t minus is a t and z, and this is t prime and z prime, if you wish. Okay, the same thing. I've just written the notation of Maldacena and Stanford. Okay, so as everybody in this know, I shouldn't bring coal to Newcastle, that this is, it is believed that, and very strong evidence that this is a model which is dual to some theory in two-dimensional ADS2, and there's a favorite action for that, which is the Jacques-Teitelbaum. Not necessarily this is the only action. It has the theory has a dilaton. This term in the dilaton, which is the change of the dilaton, gives you the part which is explicit breaking of the conformal symmetry. And this also has a black hole solution. This part, the metric is of course just ADS Rindler, because you can obtain it from the original ADS, these 2 dimensions. So original ADS by some coordinate transformation. The non-trivial thing is of course the dilaton, which has a physical significance. So the gravity sector is naturally thought of as coming from the mode of the SYK model, which is a zero mode at infinite coupling. In fact, the action which comes entirely from boundary terms is a Schwartzian action. And I should sort of mention that the Schwartzian action is quite universal, in which comes from many sources, like Gautam and collaborators show it how it comes from the Polyakov action of 2D gravity. Recent work by all of you have shown that it can be obtained by reductions of theories from 2+1 or 3+1. I mean, what is there is just the emergence of a slightly broken SL2R symmetry. That's where this action always comes from. Okay. The matter part, which are the other poles, this is an infinite number of poles of the SYK propagator, indicates their infinite number of fields, which gets reflected in the fact that the action is non-polynomial in the derivatives. However, the residues of the poles are rather complicated functions. So whatever those fields are, those fields cannot be the conventional kinetic energy terms. So in summary, the bilocal indeed provides a realization of ADS2, a Lorentzian ADS2. The wave functions which appear in the propagator, however, are not the usual ADS2 wave functions. If you are familiar with standard propagators in ADS2, they don't have those peculiar combinations of the Bessel function. They're just simple products of Bessel functions. So these have some different boundary conditions at the Poincare horizon, if you were to interpret Z as a Poincare coordinate in the Lorentzian ADS2. This I already said, that the matter fields must have unconventional kinetic energy terms because of the non-trivial residues. More significantly, and this is what I will mostly emphasize in this talk, that there is something problematic about this, because he started with an Euclidean theory when getting all these Euclidean answers, and here comes an Lorentzian ADS2. This cannot be right. I mean, Euclidean theory should have an Euclidean dual. And this is, in fact, we'll see that these 2 points are actually closely related, and we will offer a resolution of this issue.
Just to understand the point number 2, is that so the matter fields are, it's not like they are only non-minimally coupled to metric or something like that, but it's that it's just very different.
It's very different, because if we write the propagator, it's not something by just the pole. It's not like 1 upon p square minus m square. I mean, in the what representation is Kalin-Lehmann representation of the propagator, that row of thing is rather complicated, because it comes from the fact that the residues are very non-trivial.
And that translates to thing that it's not mu del mu chi, del mu chi.
No, problem. Yeah.
Something
Something very,
very
very different. Okay.
So point number 1, I might have naively thought that the weird wave functions are related to weird boundary conditions, right? Is that what?
But over here, it really didn't have a choice, because I didn't start with any ADS2. I started with some model and just, went through carefully how to implement SL2R. And what these people showed is that there's nothing you can do about it.
Right.
That's what it is. Yeah. Okay. In fact, towards the end, I'll show another reason why these functions have to appear to sort of. So far I'm doing everything at 0 temperature, but when I'll do things at finite temperature, we will see that, with the right periodicity conditions, again this thing has to come.
Why does the particular bilocal you choose have to automatically give rise to individual ADS2 wave functions? Namely,
No.
I could have tried to package the information of the
Absolutely, absolutely, I agree with that. Yeah. So all I'm going to say is it's not just a field in ADS2. Okay. It turns out, and I'll not go into the detail of this, there is an interesting interpretation of this repackaging of this infinite number of modes in terms of a 3-dimensional theory. And so the attitude I'm going to take is that I have I give you an example of the Q equal to 4 first. So what you have is a single scalar field in 3 dimensions with a metric, and this is the third direction. The third direction is an interval of some chosen length with Dirichlet boundary conditions at the end, and there is a delta function potential in the middle of that interval.
Why is the third direction?
Why is it like that?
No, why?
Why is the third direction? Right. Right. So it's sort of pretty much like Horava-Witten, where you have like two walls at the end, except you have this delta function which is sticking in the middle.
Basically, the point that your spectrum is like a Kaluza-Klein tower.
That's right. It is like a Kaluza-Klein tower. Okay.
Not a very dense spectrum.
Right.
And the delta function can also be thought of as S1 mod dB.
Horava-Witten. Right. I'll say that. Okay. Right. So why is it true? I mean, this is something. I mean, I don't know why we came up with this. We just look at the Q equal to 4 equations, and some of us were teaching quantum mechanics graduate courses, and realized that this equation does appear in some situations. They said, okay, let's try it. So the spectrum works. What is non-trivial is that. So what we do is that you solve the part of the equation in the y direction. So that gives you this number k is the quantum number of these modes. These are I've written only the even parity modes. The odd parity modes are just standard quantization. And you note that this equation is exactly the equation which determine the SYK spectrum at Q equal to 4. So you proceed more, you write down the action. Now we are doing this phenomenological model in 3 dimensions, and you can choose parameters so that it just exactly agrees with the spectrum of
So
AG.
just a minimally coupled scalar in that background.
In that background, right. What is a bit non-trivial is that if you calculate the propagator of the scalar field, this bulk propagator of the scalar field, this is an expression for the bulk propagator. Y is the third direction, and I've written out in gory detail in terms of these modes. These are the wave functions in the third directions at the locations, as you would think it would appear. What you find, so you do this integral, you get a result which exactly looks like this. I want to relate this to the SYK bilocal propagator. It turns out, and again I don't know why, is that if you calculate the propagator between points at the center, that means center of the delta function, right? So you have to substitute the wave functions of the quantum mechanical problems at the center. You get an expression which is exactly the SYK propagator. That funny, now we have a standard kinetic term. So the pole, the denominator, the propagator is standard. So the residue is trivial. The non-trivial residues of the SYK comes exactly agrees with those wave functions evaluated at the center.
I didn't understand the center.
Center means, so there is an interval and there is a delta function, this red thing here. You are solving, this is the y direction. Okay? So y equal to 0 are chosen to be the location of the delta function. So what you are doing, you are sort of calculating the propagator between 2 points on that.
Yeah, you're saying your answer has an extra variable that the SYK did not.
Did not?
You have to put in a particular value.
That's right. Yeah.
In order to get that.
Normally when we do K-wave reduction, you basically get the low energy sector to be like the low frequency, low wavelength sector in the extra direction. But this is actually mixing up all the wavelengths, right? In the extra direction. So you're putting particular values in the extra direction.
That's right. Yes. Yeah. This is not by mode by mode. This is, I think this is more like Horava-Witten, where I mean you have these heterotic theories which are living on the two end of the world brains, and if you want to calculate things in the heterotic theory, you calculate things on that, but the geometry has an effect. Or more like Randall syndrome, where I mean calculation of the propagator sticks into the bulk, but it's still a propagator on the points on the brain, if you wish. Okay.
Yeah. No, my worry was that do these modes, like are they in some sense lower energy than you're just taking 0, 0. Is there some sort of decoupling where like don't mix with these things?
I'm not sure of that. I doubt it though. I'm not sure of that.
But your aim and aim and omega sums are diagonal. So there is no mixing between the colors.
There is no mixing in the Kaluza line, but what he's saying that this object, when written in terms of an integral over the Kaluza, this object has a sum over the Kaluza-Klein momenta. It's not like only the low energy Kaluza-Klein spectrum is contributing to this. Yeah.
Because you're doing exact colors. I mean, you're not making the.
That's right. So it is asking that is there any sense in which the higher members of the tower decouple in some quantities?
And the question, what is the rationale for putting y equals z?
What is the rationale for that? It's a prescription. Yeah.
Well, it's a preferred point, and then there's eventually a brain realization.
If there is a brain realization, maybe like that, but you know, I mean, you people all tried, but I think it's, I don't know. We should revisit that problem, I think. There probably it is.
So, could I ask, suppose you took your minimally coupled scalar
Hmm.
and you did ordinary ADS CFT. So think of that interval as an internal direction,
Uh-huh.
and then you got ADS2. Now, if you now compute the 4-point functions of, so you can do Kaluza-Klein on that. So you've got an infinite number of fields.
Right.
Now compute the 4-point functions using ordinary ADS CFT. I presume that will not agree.
It won't. It won't. Right. Because the boundary conditions on that Poincare horizon are different. Okay. I don't quite understand what the boundary conditions are, but that's what it is. You know, it's a well-defined propagator in the sense that it's.
Aren't you saying, what you're really saying is, think of some geometry whose linear horizon region is ADS2 cross S1 mod V2. See, this is what is more likely, you know.
Yeah,
The
that's right.
attractive mechanism means, all right, you could get extended ADS2, extended ADSNs also.
Mhm.
But quite often you get ADS2 cross.
That's right. Yeah,
what
that's
it's
right.
saying.
That's what
Now
it's
if
saying.
it's S1 mod V2 and you just have the minimal couple.
That's
then
right.
yes,
Yeah.
like
Like, you know, you usually get an ADS2 cross on S2, say from black holes or something like that. This is sort of massaging this a little bit further.
with the only twist of being the 2 points being
Yes.
The spectrum works independent, right? And
Yeah.
just works. But now the 4-point function, if you really had your product, what you would tend to do, the S1 is that Z2 is like the S5 of the A5.
That's right. Right.
What you would tend to do is Kaluza-Klein reduce on the ADS2 and then use the usual rules of ADS2 or ADS-CFT to compute the 4-point function. And he's saying that doesn't.
It shouldn't. Yeah. I mean, even the bulk propagator wouldn't work.
Yeah, and but let's say we're not trying to identify some bulk propagator with an S5 design. I'm just going to compute the 4-point function. On the boundary, I'm computing a 4-point function, right? It's standard field theory 4-point function. I know the rules from ADS-CFT for how to.
You're talking of 4-point functions of boundary operators, as in standard area doing right. So, but that will involve some bulk propagators in calculating that, right?
I
Yeah, right.
But what I'm saying is we just use the usual rules.
Yes.
If you want to compute a bulk correlation
Yeah.
function,
You will not get this.
ADS-CFT rules, and you will not.
I don't think you'll get this.
The 4-point function will be dominated by the Schwarzschild mode exchange, and the coupling of the Schwarzschild mode to your Kaluza-Klein spectrum is just determined by the symmetries. So once you get the correct symmetry,
That will work out right. I'll tell you what, that will work out right. I think the matter part will not. I'll tell you why. See, technically the difference is the z combinations of Bessel functions and the usual Bessel functions. When nu equal to 3/2, the z is the same as j. And so, that thing.
The additional pieces are because the various Kaluza-Klein modes interact with each other and therefore can be exchanged to generate contributions to the 4-point function, right? So what you're saying is that those interactions,
Right.
see, that's not surprising.
Yeah.
I mean, all right.
It's not surprising.
What he's basically got is the spectrum, right?
Yeah.
I think it would have been very surprising had it worked because your Lagrangian is so simple and in particular is local integration.
That's right. Yeah.
Why should it be?
No, in fact, there is in fact, I think that's about the next slide, there is no reason to believe that the interactions will be local in this third dimension. I view this as a repackaging of these modes. It could be useful in things, I think. Okay. So, the one point, and this has got to do with this Gautam's comment that we did not, I do not know how this Pm equal to 3/2 came over there, but anyway, the odd parity modes did not play any role. So, maybe a better way of viewing it is to do a further mod by Z2, and that is what Witten suggested, and impose some boundary conditions on that other thing. Basically, you take that and just take this part, just one part, and this is why I do not like this. Yeah, just take this part and impose some boundary condition over here, which comes from the matching. Okay, so that is another alternative where it actually turned out to be useful later on, but let me now come back to the point of the P equal to 3/2 modes. Okay. Now, we know the non-trivial effects of this will come from the explicit breaking of the symmetry. In our case, the explicit breaking of the symmetry comes because of the warping factor in front of the third dimension, which is a function of Z. So, it is this factor which will cause the explicit breaking of something.
So it's not just ADS2 cross something,
it's a Watt product, yeah.
sorry, no, I take back what I said.
At strong coupling it is like that, but it's a Watt factor.
You need the Watt to get the spectrum, right?
Not the strong coupling massive spectrum, right, but certainly that's what I mean, the low energy part, right, you need that breaking, right, otherwise that's some trivial thing, right. That spectrum which I gave was the spectrum at strong coupling.
So that spectrum, I thought for that you just took a S1 mod Z2.
That's right, ADS2 cross S1 mod Z2.
And now you want the radius of that to change so that you get the breaking.
That's right, that's right. And I am only going to compute the breaking for the interesting mode, which is which was the 0 mode at strong coupling. Okay.
So if you say k equal to 0, that is j as infinity,
That's right.
then the spectrum that you showed in the last transparency is the leading order must be there.
That's correct. That's correct.
So this a by z will correct it to 1 by j.
Absolutely. Absolutely. Except that in that part there was one mode which was this P equal to 3/2. That's a thing that led to an infinite propagator. So we'll see what happens when you put in this correction. Okay. We actually saw already. So we compute this correction by standard perturbation theory.
Sorry, perturbation in A.
In perturbation in A, right? Perturbation in A, which is like 1 upon j, and you.
That metric is the near extremal charge, right?
This is the near extremal charge BTC, right? Right. And so we get the modifications of the eigenvalues, so that there were some eigenvalues and there are some corrections which are proportional to 1 upon j. In particular, the 0 mode has the correction which is like this, and since A is 1 upon j, this is precisely of the form which was obtained by Malthus and Stanford. So now you want to substitute this modified eigenvalue into the contribution to the propagator, and what you exactly reproduce is that enhanced propagator which I showed you. Basically it appears in the denominator as 1 upon j, that correction, and that j goes upstairs and gives rise to the enhanced propagator.
But you are calculating at precisely q equal to 4. As
Q
far
equal.
as I remember in Malthus and Stanford,
They did.
same is numerically computed for arbitrary q.
That's
and
right.
For large q, they had an analytic.
That's right, that's right, yeah.
For q equal to 4, you are giving some explicit number for that analytically.
So they have an expression which is not the coefficient, I do not know what the coefficient is, but the form of that answer, that form of the answer, they have an answer for q equal to 4 as well, for arbitrary q. There is a coefficient there which you cannot calculate
That they did
analytically.
numerically.
Yeah. That they did numerically.
For arbitrary q.
Yeah. I am not comparing the coefficient, I am only comparing the form of that answer.
He doesn't know the relationship between A and J.
That's right.
There's physically by A.
That's right.
So you can't compute it.
Okay. So that's all I'm going to say.
1 by j square in your formalism, then will you get some, can you go 1 by j square in your formalism?
I can go, I don't know whether that's meaningful because I don't know whether what other corrections to this phenomenological law model is required. Of course, you can do the perturbation theory, right? Okay. So at first we thought it's an accident which happens for q equal to 4. To our surprise, we found it actually this kind of repackaging in 3 dimensions actually happens for arbitrary q. Okay? For arbitrary q, the background is now conformal. The ADS2 part is not really an ADS2, but there is a conformal factor which depends on q. This conformal factor becomes 1 when q equal to 4. And you play the same game and you can invent a potential such that it gives exactly that that horrible thing with the gamma functions. Okay. Now don't ask me how we got this. We did reverse engineering to get this. I mean, you just recognize that ratios of gamma functions happen when you match hypergeometric functions, right? And you try to ask, cosines and sines are also some kind of hypergeometric functions. So how can you generalize this to find this answer? And with a few months of trying, we found that this actually works. Good. So I think there is something to it. I don't know exactly what it is that this is useful for.
So the delta function just gets modified by some q dependent
Potential and the delta function. Yeah. Okay. And likewise, you could do this unconventional propagator between the 2 points. In this case, it turns out that we were not able to do this analytically in the sense, I mean, I ran out of steam, my student ran out of steam in trying to find normalizations for hypergeometric functions, so we decided to do it numerically. So you calculated this because in order to compare really the coefficients which appear in the propagator, you need to know the normalizations of your wave functions, and that we computed numerically, and with some fantastic accuracy we actually found that the answer actually agrees with the SYK answer. I'll not show you how that obtains, but there is you can see this table, the numbers are quite fantastic. Good. There's something interesting about the large q limit of this model.
I mixed up data. So you knew the normalizations analytically in the SYK case? In 2-dimensional, like 1 dimension?
SYK case, there is some, for a finite q, there is some answer for that. Yeah.
Okay, so you're saying that in your case, figuring out the normalizations was hard to use.
Yeah. In the large q limit, it turns out that this there is a useful limit in which you can do where the theory of the bilocals or the Dyson-Schwinger equation satisfied by the bilocals actually becomes some kind of a Liouville theory in some sense. Okay, so the Liouville theory has a kinetic term which is standard, so there are no non-trivial residues which come along, and so therefore there is just one mode, if you wish, right? So we wanted to understand how does that appear, because we already saw that for arbitrary q there are infinite number of solutions of the spectral equations. Unlike, so if you can think of q as a kind of a parameter which is analogous to alpha prime, if you wish, it's not really like alpha prime, because all these other modes all have order 1 masses. They don't, it's not like that their masses become very large. So it remains to understand why is it that if I, for example, compute the propagator at a large q, I get a very simple answer, which has where it appears it's only this 3/2 mode. I mean, what becomes of the 3/2 mode at large q is going to contribute. And here's something interesting thing. What you find is that, so the main thing is to calculate the residues of that. So a large q limit aside a Pm equal to 3/2 remains an exact solutions, and the other poles can be perturbatively calculated in 1/q. Here I've given that answer from Gross and Rosenhaus, and you can calculate the residues of that at 3/2 and at other values of Pm not equal to 3/2. And what you find is that the residue for all these other values goes as 1/q. the residue as 3/2 is some finite answer. So in the large Q limit, the contribution of these other modes somehow drop out. Not because their masses have become large, but because in a certain sense the wave functions have become small. Okay.
So this is the residue in this bilocal point.
So if you write the propagator as a sum over poles with some numerators, that's the one. The numerators will be the residues at the poles of that spectral function, of that function which appears in the denominator. That's what I'm talking about, right?
And so this is the propagator of that scalar field limit. No, this is
Which is a statement regardless of the SYK propagator or your 3D, doesn't matter, whatever it is. Yeah.
okay.
Hmm.
And so this is the bilocal.
Bilocal, the 4-point function of fermions.
So what we are saying is that only the time reparameterization mode
Somehow survives in the Q equal to infinity limit.
has been going to infinity.
Yeah.
Anyway, the time reparameterization mode would have survived as the dominant contribution at low energies.
But,
It's a universal feature. But
right.
in addition,
yeah.
even to there's some intermediate range in energy or something.
Yeah.
Where
So what Maldacena Stanford showed is that at Q equal to infinity, if you look at the Dyson-Schwinger equations at finite J, then what you find is that you can sort of repackage that equation to look like a Liouville equation, if you wish, with an e to the, e to the phi kind of potential. And so then the idea is to take the saddle point solution of that equation, expand, around that saddle point to obtain, some kind of propagator. And so there's just one mode which is there. And I think our understanding of that is technically is that the residue of the poles of the other ones all just go away at large Q.
Sumit, at some point you had this issue about why the ADS was Lorentzian, not Euclidean.
This is the rest of the talk. Okay, right. That's in fact, I am terribly over time.
there's no time.
Okay.
I mean,
So,
lunch is
so that's the main thread of this talk now. Okay. So we have a proposal for that. So as I emphasized, nevertheless,
the bulk space, the one in which there was the extra dimension, that was still Lorentzian.
from this point onwards, you can forget about the 3D, and that was also Lorentzian, right? So forget about the 3D interpretation. Just think about just SYK and so on, right? Okay.
Moving away from the, I just, one more question. So suppose I take this bilocal. That can be thought of as some sort of generating function for the operators of the field.
Absolutely, right.
With particular coefficients related to the, presumably the difference in times between the two. Now, I was wondering whether somehow sitting at y equals 0 is giving you somehow the same generating function.
Interesting.
It's a very big question. I'm asking you.
That's interesting. And that could be. I mean, I don't know. Yeah. Interesting. Yeah. Okay. So for all the reasons which I have been emphasizing all the time, is that this space of bilocals cannot be the dual space-time in the usual sense of ADS CFT. I mean, one reason is this difference of this propagator, and in fact, so far as this difference is concerned, there was a suggestion actually to us by Maldacena that maybe one should view this as not as ADS2 but DS2. There isn't much of a difference between ADS2 and DS2. Now, I couldn't make much sense of that kind of interpretation, and since this ADS2 is a kind of a fake, as we will sort of show now, I didn't proceed any further. It's some technical skeleton space. You can think of it as ADS2 or DS2 or whatever you like. The idea was that we sort of explored that a little bit, that whether these appear as some kind of alpha vacua in the functions which appear for alpha vacua in de Sitter.
Just one more tricky question.
Yeah.
Which is that, so you were taking two fields, both at y equals 0 and y prime.
Right.
Related to the question that Sumit and
Mhm.
asked. So still you get something which is diagonal in both the frequencies, the T and Z frequencies. This is not what normally one would expect.
diagonal and the
If you
T.
take the two fields at y equal to 0 and y prime equal to 0, the field at y equal to 0 is already a sum over the Fourier modes
Right.
with all kinds of sums. And the field at y prime equal to 0 is another independent sum over the Fourier modes with all Fourier modes.
Yeah, but that's because we are expanding the field in the basis which are eigenfunctions of the part of the Laplacian in the third direction. So the propagator between the third, the Kaluza-Klein momenta, if you wish, are diagonal in the momenta. See, that part of the Laplacian can be independently diagonalized apart from the ADS2 part. Make sense? I think so.
I just want to kind of 1 minute.
Yeah.
You know, this generating function, this bilocal, in a way is in our heads. Because the operator spectrum of the theory is just particular operators,
Agreed.
and the data is the 2-point function of these operators. So I'm asking, I'm not sure, but that you're matching this 4-point function, is it matching of something physical or is it matching of conventions? Meaning the 4-point function is just encoding 2-point functions of various operators. Right?
That's correct, yeah. Yeah.
And your 2-point functions are going to come out right because you've got the spectrum.
Well, there could be getting the spectrum right, but there could be numerators which are non-trivial.
But operator by operator, that will just be a normalization. It's putting them.
I see. So it is actually comparing to preferred normalizations, if you wish.
Exactly. Preferred normalization, which is basically the normalization that occurs in your generating function.
Yes, I think so. Yes, yeah.
So it's a question of somehow conventions. I mean, it seems to me that the question of physics would be getting the 3-point function of these operators,
Right.
which would be 6-point functions of your.
Yeah, but the 3-point functions, I'm pretty sure, cannot be obtained by a local interaction. So I don't think there's any. He's saying at the end of the day, you're calculating some 2-point functions of some CFT, and the normalization is never fixed in a 2-point function, right? So I think it's only CIJKs which are.
I thought what you were doing was you were looking at your bilocal field,
Right, 2-point functions of that.
and you looked at the 2-point function there, and you were trying to interpret that in terms of some higher dimensional geometry, right? ADS2.
That's right. Yeah.
And fantastic it works, and I don't know what it means. But I just want to understand from the point of view of ordinary ADS. So this bilocal field, from the point of view of a CFT, is just some generating function of operators of the theory.
Yeah.
Because the coefficients in the Taylor expansion will give you different operators. So what you have is an infinite number of operators with different scaling dimensions, all of which are packaged together in this bilocal. Now how you package it together is up to you. In ordinary ADS CFT, you would take each of these operators, compute their 2-point functions, their 3-point functions.
Right.
The 2-point functions are sort of guaranteed to work up to some normalization because you've got the spectrum.
I thought what we were trying to ask is there a repackaging which admits in a natural sense the higher dimensional interpretation, right?
Right. So he's saying that once you get the spectrum right, then you will get these 2-point functions right. Up to a normalization, because the normalization is something you cannot fix.
Yeah. Now the thing that is non-trivial is that the coefficients that appear in the generating function in the bilocals are also reproduced at y equal to 0.
That's right. That's it.
And that's fantastic, but it's not so clear that that's physics.
Yeah, I understand that. No. Maybe I can rephrase this. It's like some n, some mu1, t1 up to tn, suitably done so that they become primaries and so on, right? So this is what is z. So if you calculate phi, you write it this way, and you can extract out the 2-point correlators of these operators by identifying the right power of z. This is one way of doing it, right?
So this equation is
that's true,
Let them
right.
complicate some other operator and give the OP equation.
But we're not supposed to think of phi.
No, no, no. Phi is just a field.
Oh,
So we should think of
function.
Phi local, the contraction itself is the basic of it.
Yeah,
This is mistake I was also making in my question earlier. Shouldn't think of it as 4 point, it's a 2 point.
yeah. It is really a sum of various 2-point functions. Right, yeah.
but in we usually take the 5 per data, right? In the chaos calculation.
Yeah.
Like your phi is actually the chi of SYK.
But if you want to use, yeah.
Sorry. I'm a little bit confused now.
You see, if you want to use area CFT, then isn't the field in the bulk corresponding to the operator? There's only bulk.
No.
Right, so suppose
I-
you do area CFT, you should only associate operators with the
I thought if I go back to your first transparency, where it was a very simple field theory model, the free
Yeah.
flowing model, the attempt was, can we repackage the information about that model in a way so that the ADS isometries come out naturally?
Right, that's right. Yeah,
If
yeah.
we could have done that, then we would say, all right, we are somehow understanding the emergence of the extra dimension.
Right.
Now, I thought you were trying to do the same thing for SYK.
Right.
Repackage the information of the SYK
Right.
in a way so
Mhm.
that the ADS2 isometries with perhaps even the breaking comes up.
Right. Right. And in doing that,
So that's not, I mean, I agree, there's a lot of guesswork there, but isn't that roughly the attempt here?
it is. I think his question got to do with the matching of the 3D model with the SYK model, not with this. He's asking, yeah, what is the significance of the fact that at y equal to y prime equal to 0, that propagator exactly agreed with it. That's what he's
Fine,
asking.
But I guess for this part of your talk, I thought that's not so
Okay,
important.
let me go to the next part of the talk. It's a little more interesting. So I think because everybody wants to eat, I think.
But aren't you here back to your original motivation of just taking the SYK and trying to see whether you can obtain an additional dimension out of it?
Yes, yes, yeah.
It's not so terribly important that it came out of a 3D.
No, it's not terribly important, right?
This was just my
Yeah,
wailing.
yeah. Okay. So now we're going to ask, how come we ended up with a bilocal space which is Lorentzian? And this is something very funny because in 2 dimensions, both the Euclidean and the Lorentzian ADS have the same symmetry group. You can write it as SO1, 2 or SO2, 1, which is of course the same group, right? That's why it happened. Okay. We will now argue that the bilocal fields should be related to standard fields in ADS CFT, but so as I said, you should get a theory in Euclidean ADS too somehow, and we are going to argue that there is actually a relationship. It's quite a natural relationship between the bilocal field and fields in ADS2, but there is a non-local transformation which actually has a nice understanding. Okay. So to do that, let me first note that here I have written down the metric on the bilocal space and the isometries of this metric, which I have written in terms of T1 and T2 rather than in terms of T and eta, but you can read at that in T1 and T2. And this is the metric of an Euclidean ADS2 space where I have written down the various isometries, the D's and the P's and the K's of that. Okay. They are written in terms of this, the coordinates and their conjugate momenta in phase space. So P1 is del del T1 basically, and P2 is del del T2, and so on. Okay. At this level, we are just doing a classical thing. You can think in terms of Poisson brackets. And you can ask, is there a canonical transformation which takes these generators into that generators, these generators into those generators? At first sight, it almost looks impossible that you can have that because there are just too many conditions, and you must have the right canonical. There are just too many. T comma T has to be 0, T comma P has to be something, and for reasons which I do not know, the answer turns out to be yes. And this is the canonical transformation. You can just sit down and substitute that in, and this will take you from one to the other.
Sorry, what is this taking from one SO 1, 2 to the other?
It is taking, I want to make a coordinate transformation in phase space between T1, T2, P1, P2 to tau z, p tau and pz, such that this becomes that. Okay? It's a point transformation for the momenta, it turns out, and you can sort of utilize this with a little bit more and find actually what it means is that a function of tau and z are the coordinates in Euclidean ADS2. Starting with that, you can invent a function which functions on Lorentzian ADS2 by this kind of formula. This formula is actually a well-known transformation. It's called the radon transformation. And so
What is the still not quite got it. What is the characteristic of relating the function in terms of tau and p can be like this? I mean, that is, wait, these are two different, one is Euclidean ADS2 and the other is
Lorentzian ADS2, right?
I could have done something very simple. I could have said take tau to IP.
Yeah,
Relate.
you could have done that,
You're
right?
not doing it like
I'm
that.
not doing it
So
like that, no.
What is special about this?
So what is special about this? I'll maybe wait till the next slide.
Sorry, usually in the radon transformation we take some function of the Rita-Kanagi.
Just wait.
Okay.
There's no Rita-Kanagi. It's a geodesic. In this case, just. I mean, there's no nothing more. It's simple. So this is the idea of creating a space from the space of geodesics, basically. That's the, I think it has a name called integral geometry or whatever. This has been used in the past by particularly Bartek, Czech and collaborators to give a kind of a covariant formulation of the HKKL. You know, that's not the way we are using this. We are using some mathematics which are associated with this.
So, how did you come from the last slide to this one?
Which last line to this one?
The previous slide.
The previous slide was the definition. This is the definition of the transform.
I mean, in the sense that if the fields are defined like that,
Yeah.
then the canonical transformation okay,
Right.
and then now what is it saying?
Okay. So now I'm saying that what is this transform? What this transform does, so this is the upper half plane of Euclidean ADS2. What it does, it takes a geodesic which joins 2 points on the boundary. This is the red geodesic. So what you're instructed to do is to take a function which is defined on this upper half plane, restrict it to the geodesic and integrate over the geodesic with an invariant measure. So you get a function which is a function of this, of the two ends, because that's what characterizes the geodesic, and that's what I call the radon transform. If you use explicit coordinates like Poincare coordinates for the upper half plane, you get that formula. This delta function thing is just the thing which is telling you the geodesic. Okay. This, yeah. No? Okay. So why is this? Because this has the interesting feature that it intertwines between the generators of Euclidean ADS2 isometries and ADS2 isometries, which leads to the fact that a radon transform of a Laplacian of a function is a Laplacian of the other Laplacian acting on the radon transform. Okay. So it sort of so there are two things. One is this, and it and in the fact that it sort of gives rise to Euclidean space from a Lorentzian space, and vice versa, is the clue, is the sort of a clue which we take in order to proceed.
Just to connect with what I know from earlier stuff, is there a similar equation in the ADS3 case where they
Yeah, there are two factors of DS2,
okay.
because there is a Z and a Z bar.
Okay.
There is none like that. It's just one of those. Yeah.
Okay.
The physical use of that is very different from what we are doing. This is just math. Okay. Good. So
Sumit, the stuff that Sandeep said, that is just two
I'll tell you why that doesn't work.
Ah.
Of course. It seems like I've answered to a lot of your questions. Okay. Good. A test of this proposal would be the following fact. Does it actually take the correct eigenfunctions of the Euclidean Laplacian operator into those funny z nu functions which we encountered? Because the Euclidean Laplacian operator just has a unique set of normalizable modes, eigenfunctions, right? Those are the k, the modified Bessel functions or something. So the question we are going to ask is that, does it take that into what happened in the SYK from some completely different considerations? Okay.
That would explain your boundary conditions.
That will explain that will explain the boundary. I don't know whether it explains, it sort of shows some kind of consistency with that. And
Those came out of whatever Polchinski or Houseware's solution, right? Or
those came out of the fact that there was a particular kernel which needed to be diagonalized. That kernel was invariant under SL2R transformations. So the idea was to simultaneously diagonalize that kernel with eigenfunctions of the Casimir of SL2R. Now there are many eigenfunctions of the Casimir, like the combinations of Bessel functions, but what this Polchinski and Rosenhaus, probably Kitaev also showed, is that if you carefully look at what combination of these eigenfunctions actually diagonalizes the kernel, I mean just some subtle boundary terms which don't ask me, I mean I won't be able to tell you, it is this combination. So it was tied to SYK somehow, I mean the fact that it kernel.
so it was a presumably well-posed problem.
It's a very well posed problem. Yeah,
Solved
right.
problem.
Yes, yes.
From the field theory. But there was no bulk interpretation.
There is no bulk interpretation of that.
Now we get a bulk interpretation.
That's
And you do the normal thing in ADS, in Euclidean ADS, and the transform you do.
Absolutely. That's what the claim is. Okay. And so, fishing around with Gradstein-Reitzig for quite a long time, this is what you get. So these are the Euclidean ADS eigenfunctions of the ADS2 Laplacian. These are k's with IR. You know that's you can check that these are the right eigen. Oh, you're a class. Oh. Sorry. And if you use those, run your machine, do that integral can be explicitly done, and lo and behold you precisely get this combination of the z nus. Rather irritatingly, you get these things as well. Okay, I mean whether these are meanings or not, I don't know. We might try to give them meanings. So at the end of the day, you plug everything what you got into the propagator and you get a horrible expression. And the horrible expression, and again I don't know what this means. There is a piece. Okay, these are comes from the residues of the poles. This part comes from the Euclidean propagator of a field. That's the usual k times I which appears in Euclidean propagator. And then there is an additional contribution to all this, and the whole thing uncannily looks like the 2-point function of what are called macroscopic loop operators in the C=1 model. And there they have been sort of speculate, completely wild speculation that there may be analogues of something like discrete states in this model as well. Namely, even in the graviton-dilaton sector, maybe there are something. I don't know. Okay. Another test of this idea is to see what happens at finite temperature. The way you do finite temperature strong coupling is to make a reparametrization which compactifies the time direction by this. And you might have thought, see, it doesn't work. And you might have thought that doing this to the standard metric in bilocal space will land you up into a black hole metric, Lorentzian black hole metric. It doesn't. What you land up is this. The Lorentzian black hole metric is that. Okay. This looks like global ADS2 with some identifications. The identifications caused by the fact that this is an angle. So it's a pretty weird space. So you might ask that So, I mean, you again redo what you did for the radon transfer for this geometry. These are the explicit formula for those radon transform. And what we are going to ask now is that if I take the standard modes of the Euclidean black hole Laplacian with something, those are fixed, completely fixed by the periodicity conditions now. Okay? So, those have been worked out by Maldacena and Stanford. These are some hypergeometric functions, and you want to see if I take this and do a radon transform, what do I get? Sorry, I'm extremely sorry. So, this is not the Euclidean black hole. So, these are the eigenfunctions of that metric, this metric. Okay?
It's not black hole.
They're not black hole. And you want to compare it with the unique eigenfunctions of the Euclidean black hole, which are again some, what are these called, associated something or the other. And again, we don't know how to calculate the normalizations. So, we calculated numerically the radon transform of this for some values of the parameter and compared it what was there in the other hypergeometric function. The other was the eigenfunctions of the Laplacian with identification, this one. It does. That's where this comes from. This is the eigenfunction, that's the spectrum. Yeah, this is the correct eigenfunctions of that. And in fact, you can check, this is yet another check. This is a completely regulated problem now, and you can take the you can take the zero temperature limit of these solutions, and you get in fact these zeros. Okay. So I think anyway, let me just end by saying that we don't understand the whole story, but I think our hope is that the observations will play a useful role. In particular, because of the necessity of this rather non-local transformation, we'd like to know whether we could actually learn something about in emergent black hole geometry from the finite temperature part. That's what we're working at the moment. Okay, let's go.
Okay. Any urgent